This has been a really wonderful week. I met many of my old friends here. It's really nice that many of the very top people in my field, they attended this conference, and also together with many younger people, I made some new friends also. Some of the speakers and participants I had never met before, but it was great. And I also met a lot of students here. I talked to them. That was also really nice. So I know that the organizers spent a lot of time organizing this, so I would like to thank them again, but I think all of them already left. Oh yeah, Edward is here, so he's a representative. Yes, and I also like to thank all the speakers and participants, because I know at this time of the year it's not easy to travel. So almost everyone I talked to, they said they had to make some arrangement for their teaching. So I would like to thank everyone. I know it's not so easy to travel. And thank the director again for organizing this, not only this year, but it's a tradition every year. Okay, so now let me go into my talk. So it seems there are a few people maybe who are not algebraic geometers or not maybe experts. In the beginning, I will go through a few slides, very general remarks about algebraic geometry, and then I will go into a little bit more advanced stuff. So as we all know, algebraic geometry is basically about polynomial equations, about the algebraic and geometric structures that come out of polynomial equations. Recently, I just tried to learn a bit about the history of mathematics, and it's amazing to see how much polynomials they play a role in the development of mathematics throughout history in the last 4,000 years. Many of the greatest breakthroughs in mathematics are related to polynomials. For example, solving equation in one variable, that already took like 4,000 years to develop. And finally, it was solved by Galois theory, and that is already the simplest type of algebraic geometry, which took like 4,000 years. And then in the ancient time, already people started to look at not only one variable, but multivariable polynomials. And then, of course, the ancients didn't have algebra, so they couldn't do too much. But later on, in the 17th century, when people like Fermat, Birkar, Newton, they came into the scene, they actually did a lot of algebraic geometry, although we may not think of them as algebraic geometers. I mean, when you say Newton, you always remember calculus. But in fact, one of the important works he did was classification of cubic curves. That is one of the, just one of the one-dimensional kind of algebraic varieties. Anyway, I don't have too much time to go into history, but algebraic geometry or polynomials has been a very central area of mathematics since the start, really, of mathematics itself. So it's more or less all about polynomials when you look at it from an algebraic point of view, but the nice thing is that the geometry also comes into the picture, and that's what makes everything exciting. On one hand, we have algebra, on the other hand, we have geometry. Now, in this talk, for simplicity and also for good reasons, I will consider our ground field to be an algebraically closed field of characteristic 0. But at least in lower dimension, we know many things also about characteristic, positive characteristic. So I noticed that the online, in order to record it, someone has to press something. Otherwise, I think it will not record. Is it? I think you need to like press got it or something. No. Okay, thank you. Okay, so let's work over, you could just take complex numbers if you like, it will not make much of a difference. And let me just remind you, at least for the young people, in algebraic geometry, first we usually start with a local picture. We look at, first we look at a polynomial ring given in a finite number of variables over our field, and then an affine algebraic variety is just the common solution set of finitely many or infinitely many polynomial equations. We think of the solutions as points in inside some affine space, which in this case will be just the ground field to the power of the number of variables. And the nice thing is that everything about the geometry of this space is encoded in a ring, which is just the polynomial ring divided by the ideal generated by these polynomials. So that's where this dictionary of algebra and geometry comes from. And that the goal here is to understand the local geometry of this type of spaces, in particular to understand their singularities. So there is a big difference between algebraic geometry and differential geometry. In differential geometry, locally all spaces of the same dimension are the same. There is no difference. But in algebraic geometry, even locally, there are huge differences. Even in low dimension, we have to understand what goes on locally. And thus makes life difficult, but actually makes it also exciting. And there is a global picture here. So in general, in mathematics, it's much easier to work with compact spaces. That's because you have all the limits of the objects present in the space, so it's much easier to look at them. And in algebraic geometry, to compactify spaces, we work in the projective setting. This is basically just the usual affine space compactified. But more precisely, it can be defined as in the slides here. And then the goal, so again, we can look at polynomials, at least those which are homogeneous. We can look at their set of solutions. It will give you some geometric space. And then the goal is to understand the global and also the local geometry of these kind of spaces. Now, since I said for simplicity, we work over the complex numbers, then these spaces, if they are smooth, they are also a complex manifold. So then there is an immediate interaction between differential geometry and algebraic geometry. Okay, but so what is the big problem here? The big problem is to, as I said, to understand these spaces. But in practice, that means to classify these objects. You can ask the same question or consider the same problem in every area of mathematics, even outside mathematics. You want to classify things, for example, in biology, or you want to classify people, put them in different classes according to certain characteristics. It's the same in algebraic geometry. We want to kind of put algebraic varieties into different baskets and say everyone in this basket, they are similar in some way. For example, for people, you could say they all have, I don't know, high school education, or they all have this much salary, or they have this kind of background, and so on. In algebraic geometry, we can define some invariants, some objects can be just a number, or it can be an algebraic object like a group or something geometric, and then we try to distinguish these spaces. But in order to distinguish these spaces, you need to relate them to each other in some way. And in algebraic geometry, these are done by maps or morphisms, as we usually call them. In group theory, you will have group homomorphisms. But in algebraic geometry, we have morphisms. And the key point is that these maps are all defined by polynomials or something related to polynomial. So algebraic geometry is basically about the world of polynomials. Okay, and then this classification, it has a long history, almost 200 years. Well, if you go back to Descartes and Newton, of course, is much longer. And then people have realized for these several hundred years that there are some special classes of algebraic varieties that play a key role. And the interesting thing is that these kind of spaces, they also show up in differential geometry. They also show up in arithmetic geometry. They also show up in other areas of mathematics for their own reasons. But in my area in algebraic geometry, and more specifically birational geometry, they also show up in a very natural way, and they are of fundamental importance. And as we will see in a few minutes, they are like the building blocks of the algebraic geometry world. So let me just remind you of some terminology in this conference. These were already mentioned quite a few times, but for those who didn't attend the other talks, suppose I have X, an algebraic variety. It may be smooth without any singularities, but we often allow some type of singularities. Those we can manage somehow. And then we say this X is Fano if its canonical bundle is completely negative or anti-ample. We say it's Calabi-Yau if its canonical bundle is completely trivial, and canonically polarized means completely positive. In the sense of differential geometry, in the language of differential geometry, the first category are the spaces with positive curvature. The one in the middle have zero flat curvature, and the last one have negative curvature. So there is a direct connection between this object canonical bundle in algebraic geometry and curvature in differential geometry. Now, just as example, if you look at a hypersurface of degree r in a projective space of dimension n, then you can see immediately which one of these categories you have. It just depends on the degree, basically. The picture is very simple. But the problem is that in general, algebraic varieties are not defined by one equation. They can be defined by many equations in a large dimensional, maybe projective space, and so distinguishing these categories is not so easy. And another problem is that a typical, a randomly chosen algebraic variety doesn't fall into these classes. So that's why I call them special classes, because they really are very special. However, in dimension one, similar to hypersurfaces, the picture is very simple. Every smooth algebraic curve is in one of these classes. So automatically will be Fano, Calabi-Yau, or canonically polar. Okay, but that's not the case. In starting with dimension 2 is not so simple. Now, one of the most really fascinating problems in the whole mathematics, not only algebraic geometry, has been the following conjecture, or maybe I divided it into two problems. You may not see these things on the list of clay mathematics problems and so on, but I think that is equally important. It's probably even more important because it has led to a huge amount of progress in mathematics, unlike some of those other problems. So what these problems actually combine several problems together just for simplicity. What they mean? What are they saying? It says, suppose that we start with an arbitrary algebraic variety X. First, we have a machinery of resolving the singularities. In some way, we can get rid of the singularities and go to the smooth world, which is similar to differential geometry. And then there is a program which we call it minimal model program or Mori program. So fortunately, Mori is here sitting in the audience. And this program says that you can transform this space by a precise recipe. So in fact, it just really looks like an algorithm. It tells you in every step what you should do. And then if you are lucky enough, if you can show that after finitely many transformations, that you will get a new space that I call it Y, and this Y will satisfy some very special properties. So the original X can be quite wild and complicated, but the end product should have a kind of not simple, but a much better kind of geometric structure. So we start with X, and then we end up with Y. If everything in between works, then in the end, this Y, either it will have trivial, it will have positive curvature along some fibration, or it will have trivial curvature along some fibration, or it will have total negative curvature everywhere. And that is an amazing statement, that you can transform every arbitrary algebraic variety into one of these forms, because each of these classes are quite special. Now, if one can carry out all these programs successfully, then in the end, what you do is try to understand the end product as much as you can. In other words, to classify the Y at the end. So this whole thing is telling you that there is a recipe for transforming your space so that in the end, the spaces that you have to classify are much simpler in a way, much better behaved than the original one. And if you can understand these end products, at least in theory, you could go back step by step to the original variety and understand that variety as well. And trying to prove that, for example, the first problem, the conjecture actually is true, this already involves a huge amount of local, global phenomenon, conjecture, statements, and it's just really very interesting. And it also connects to so many other areas of mathematics. So I kind of squeeze everything into this one page, but if you want to do this, even in dimension 2, it takes a huge amount of work. Now, I just give you a historical summary of what we know so far. So this thing actually started already in the 19th century, around mid-19th century. Well, there is also dimension 1, which I kind of didn't write it here, but dimension 1 basically was, I mean, already goes back to the old days, Fermat, Descartes, Newton, and so on. And then a huge step was taken by Riemann in the 19th century. He basically classified those varieties of dimension 1. And then people, not too long after, especially the Italian school of algebraic geometry, they started to imitate Riemann's ideas to extend it to dimension 2. And they did it with great success. I was reading a book about history of algebraic geometry, and one of the sentences say that starting with Riemann, everyone started to do birational geometry. So this kind of area, program that I talked about, is specifically called birational geometry. It's one area of algebraic geometry. So these Italians, they did a lot of work. More or less, they classified these two-dimensional algebraic varieties, but there are also a lot of work later on in the century by Zariski, Kodara, Shafarevich, and so on. But so already by the turn of 20th century, people understood what the geometry of two-dimensional spaces look like. And then they tried to extend that to dimension 3. But they realized this is extremely complicated. In fact, they didn't know even what to do in the first step. In dimension 2, the picture is kind of, at least this algorithm I mentioned is not so complicated. But in dimension 3, people had no idea how to take that first step until Mori came in the late 70s and told everyone what that first step should be. And then there was an explosion of activities in the 70s, which partially started even before Mori in different areas around the world. And by the early 90s, there was a good understanding of geometry in dimension 3 due to work of many people going back actually to the 60s and even before. And then there was a period of really kind of very slow progress about from early 90s to early 2000, where again there was another explosion wave of activities, starting with Sokurov, then Heiken McKernan. McKernan is also sitting there. And then there were other people involved, and then now we have at least a partial understanding of this program in every dimension. But by no means this is a full understanding. But there were big steps taken by people that you see. And there are many other people that I didn't put. Now, in order to do all these things, there were a few fundamental ingredients. So I will just say a few technical words. One of these things were about, again, that first step, what you should do. These were done by, on one hand, by Mori, and on the other hand, by Kawamata and Sokurov, using quite different techniques. And then in dimension 3, so Mori took one of the big steps, and then later on dimension 4, there was Sokurov and Heiken McKernan and so on. Okay, I think that's enough for the history. And then one of the main statements that is at least easy to state, but there are many other things involved, but at least there's something that I can state in one line. It's one of the outcomes of this progress in dimension, in every dimension. It was done in this so-called BCHM paper. BC just means B is Birkar, Cassini, Heiken, McKernan. And it says that there is an algebra, an algebraic object that you can attach to every algebraic variety. And the statement says that this algebra is finitely generated. It's as an algebra over the ground field, let's say over the complex numbers, is generated by just finitely many elements. And this is a very strong statement. It implies it has many nice geometric consequences. And I'm also happy to say that at this symposium, for the very first time, these 4 people came together in, well, we were in one room once before, but we were never on the same lunch table. So that happened for the very first time. Okay, so I do not have too much time. Now, one of the things that comes up in this whole story is related to singularities. Singularities, basically, we cannot just avoid them. We have to treat them. We have to deal with them, and they actually make things more complicated, but at the same time more interesting. So let me. I think it's difficult to really say much meaningful stuff about the singularities unless you already know singularities. But just very quickly, the way we look at singularities in this part of the world is by taking a resolution of the singularities. In other words, to try to remove the singularities. Fortunately, we have one expert of resolution of singularities here, Edward, who actually I have been talking to him recently, because although we know resolution of singularities for a very long time, but some form of it actually is kind of, it was done later by Edward and some other people. Anyway, so here are some examples of the type of singularities you could encounter. For example, if you take a rational curve, just means the projective line, and then you can build a cone on top of that. Very similar to building cones in topology. And then you, in almost all cases, you get a singularity. And then you can calculate everything about these singularities. And those are nice singularities. But if you build a cone over an elliptic curve, you still get a reasonable singularity, but that will be actually more complicated. But if you build a cone over a curve of genus 2 or more, then you are going out of the category of singularities that we usually work with. Okay, maybe just keep in mind that singularities are around and we don't necessarily try to get rid of them. I defined for you or mentioned these three important classes: Fanos, Calabi-Yau's, and general type. And I'm going, if there is enough time, through these classes and just tell you a few things that we know from our point of view. And I'm not going to give a survey of this. Actually, to be more precise, I will mostly talk about my work. So apologies if you don't see your work mentioned or your name somewhere. There are too many things to really mention, so I'm sure I couldn't mention everyone. Okay, suppose now we look at Fano varieties in every dimension. And then on Fano varieties is the anti-canonical divisor, or the minus of the canonical divisor, which has some positivity. And then in algebraic geometry, if you have a line bundle or divisor with positivity, that's a kind of natural thing to play with and to try to understand it. And one of the statements in this direction, it says that if we work in the same dimension, and if you look at all the Fano varieties of this dimension with those reasonable kind of singularities, then you can find a number n depending only on the dimension, such that minus n times this canonical bundle, it always has a section. There is always something non-empty about this divisor. The precise statement is, it says more than this. It says that you can always find some nice element. So you may have many objects in the system given by this divisor. The statement says that you can even find, first of all, this is not empty. Secondly, you can find some of them which actually look very nice. So for example, if X is the projective space, let's say projective space of dimension 2, you could take a cubic in the anti-canonical system. That is one choice. It's not the only choice, but that's one of the possibilities. But if you consider other Fano varieties with complicated singularities, then finding this looking at this kind of system is not so simple. And this was conjectured by Shokurov in the 90s. And then not long after that, there is another result which says that now if we look at all these Fanos of the same dimension, and if we put some control on the singularities, not allow kind of to be too arbitrary, then the number of these spaces can be parameterized by a finite dimensional or finite type kind of space. So in other words, you may have many of these spaces, and indeed we have many even in dimension 2, but it cannot be like just too much. There is some kind of finiteness about this set. And in algebraic geometry, if you have a family or class of objects which is it has this kind of finiteness properties, then immediately it implies that almost all the iron variants that you associate to these spaces, they will fall into a finite set automatically. And that you can use for classifying these spaces or for proving many other related statements. And this was conjectured by Borisov, Alexeyev, and Borisov. There are two Borisovs because they are brothers. It's not the same person. And then a kind of corollary of this, which was discussed a few times in this symposium, is that is related to algebra, which you can formulate it in a purely algebraic way without any mention of geometry. But I wrote it in a slightly geometric way. It says that if you look at the birational automorphism of Pn, now, if you are not familiar with this kind of terminology, this is basically the Galois group of the field which is generated by n variables, n independent variables. It's just the Galois group over the base field. So it's a purely algebraic object. But this group has some very nice properties, and this property is called Jordan. And roughly speaking, well, precisely speaking, it says if you take any finite subgroup of this group, it's not very far from being abelian, in the sense you can always find an abelian subgroup of index being universally bounded. So this was proved by Prokhorov and Shramov, assuming that you have the second, the theorem in the middle. So they did their work actually earlier, and then once I proved this one in the middle, then you got this for free. And this was conjectured or maybe written down as an equation by Serre, who checked it for the case n equal to 2. Okay, so this is just one of the corollaries, but this is not the end of the story. In fact, I may be, unfortunately, not enough time, but this kind of statement is related to many other kind of problems or areas or directions in algebraic geometry and beyond. So maybe I just mention a couple of them. So after this work, then there were many other work. It just led to many other developments in the study of linear systems on algebraic varieties, Fano fibrations. I'm going to talk about that a bit more. And then Calabi-Yau varieties of fibrations, and also a much larger, wider class of algebraic varieties. Unfortunately, if you are not familiar, it's difficult to define this terminology now. And then relate to moduli of algebraic varieties of types which are not even Fano. That's the nice thing about this story, that it actually, in the end, it leads to constructions or statements of varieties which they don't look like Fano at all. And then a structure of singularities in many different ways, many different points of views, topology of singularities, I don't know, explicit classification of varieties in dimension 3 and 4. Explicit here means that you just don't say there exists a number satisfying something. You really want to pin down an explicit, a precise number, not just existence. And this kind of statements actually are very hard to prove. Although many theorems we have about existence of some object, some number or whatever, but when you try to make it effective, and then you end up with a lot of difficulties. But there has been a lot of progress in the last couple of years. And then another story which was well covered in this symposium is related to Fano varieties with case stability. This kind of thing originates from the world of differential geometry. It's related to existence of metrics and so on. And there are many people working in this direction. Some of the main experts are here, like Chengyang Zhu and his collaborators. And the stories of Fanos, obviously, because they're all about both are about Fanos, so they're naturally related. And then I mentioned these birational automorphism groups. I mentioned the result of Prokhorov and Shramov, but there were later also developments. For example, if I go back to the previous page, where I defined this Cremona group, it was a question from a very, very long time ago, whether this group is simple or not, whether it has any non-trivial normal subgroup or not. And it took a very long time to answer this question. And the answer in the end is actually quite geometric. And one of the crucial ingredients is this statement about Fano varieties. And then there are other developments about irrationality of, like estimating irrationality of degenerations of Fano varieties, but also more general. I think that's enough. I'm not going through the whole list. So just I wanted to say that there has been a lot going on in the last 6-7 years. Okay, this one is a bit more technical. It's really for the experts. One of the structures that come out in the last about 10 years, we call them generalized pairs or generalized spaces. They are basically what they are. They are an algebraic variety together with some positivity on some birational model, some meromorphic model. So the positivity may not live on the same algebraic variety. It may live somewhere far away, but related to the algebraic variety. And this kind of thing actually come up very naturally in algebraic geometry. But in the last 10 years, there has been a systematic development of this type of structures. And it is related to many problems in algebraic geometry. And the list of applications just keeps growing and growing. So here I just told you, listed a few of these things. For example, if you want to study a space which has a Calabi-Yau fiber structure, which comes up very, very frequently in algebraic geometry, then these kind of structures immediately come into the picture. So if you want to understand any space with a Calabi-Yau fiber structure, you immediately can look at these generalized spaces. And then it has been very helpful to understand Calabi-Yau varieties. Moduli is actually a very crucial ingredient of construction of moduli for some classes of varieties. And then more recently, people have even applied this to the birational geometry of Kähler manifolds and also foliation theory, which was the subject of the previous talk, and so on. So let me skip this quickly. Okay, so I told you something about Fano varieties, this finiteness statement, and so on. But one of the outcomes of the conjectural program that I told you some time ago is so-called Fano fibration, or we also call them Mori fiber spaces. So these are spaces where along the fibers you have positive curvature. And then naturally we want to understand this kind of spaces. Now, what I wrote here sounds kind of very technical, but let me look at, it was conjectured by Shakurov. It will be easier to look at some of the corollaries. The first corollary says that suppose I have one of these Fano fibrations, and I have some good idea about the total space. For example, it has some kind of singularities that is kind of controlled. Then you could ask what happens on the base. Because if you want to understand these spaces inductively, you have to understand the base. This is very natural. And another thing you have to understand is the fibers. So in general, if you have a fiber space, you need to understand the base of the fibration and the fibers. And this corollary basically is telling you that you can understand or in some way control the base. It says if upstairs you have a certain type of singularities, then downstairs you also have another maybe wider type of singularities, but everything is controlled. It cannot be like too wild. And so once you have this statement, then you can immediately apply induction to understand your algebraic variety. So these are actually very new. It's just were completed this year, and this particular corollary was conjectured by McKernan. Some special case of this was already proved by Mori and Prokhorov in dimension 3. The second theorem, or in some way corollary of the first statement, it looks totally different. It says the following. Suppose we look at spaces which are not Fano, but in some way, in some weak way, they look like Fano. The big difference is that in the case of Fano varieties, the anti-canonical system is completely positive. But here we are looking at a class where you have just a weak kind of positivity. But on the other hand, these spaces are rationally connected, which means they contain a lot of rational curves, a lot of images of the projective line. then this statement says, again, if you control the dimension and type of singularities, you have some kind of finiteness involved. So in some way, these are more general than Fano varieties, but for example, one place where they can appear is when you take the limit of Calabi-Yau manifolds. You can have this kind of limit where you have a Calabi-Yau which is actually singular and it doesn't quite look like a Calabi-Yau, but you still have to understand them. And this one was conjectured by McKernan and Prohor some time ago. So maybe this is a good place to stop for any questions. Well, it is not the end of the talk. I'm just saying if you have any questions or not. Okay. So I kind of had confusion when I was preparing this talk. Before I arrived, I thought there will be a general audience, so I said, okay, I'm going to prepare a very general talk. And then during the conference, actually, almost everyone was kind of expert or semi-expert in algebraic geometry. And then people had to talk about more technical stuff. And then I said, well, I am the last, giving the last talk, and the same people will come, so I will prepare something slightly technical. Unfortunately, even though this is kind of general in some way, but it may look like technical to you. Anyway, so far I talked about Fano varieties, and now I go to talk about another class. Remember those three classes of varieties. One of them is called canonically polarized, or kind of general type. In dimension 1, these are just curves of genus at least 2. And we like to classify them naturally to understand them. And then there has been a lot of work in this direction, which says if you fix certain invariants of these spaces, then you can kind of parameterize them. So in algebraic geometry, parameterization is very important. Here I write some examples, but I'm not going to read them. Now, to be more precise, if you fix the dimension and if you in some way fix the size of the canonical bundle, which we call volume, but you can think of it as some sort of measuring the size of this canonical bundle, the statement is an important result of Haken, McKernan, and Drew, which says, again, there is a finiteness property here that you can parameterize all this by some finite type space. So the simplest form of this is if you fix the genus and if you look at all the curves of the same genus, then they are all parameterized by one, actually, algebraic variety. In higher dimension, you may have like many components, but it's still a kind of controlled finite type space. And then work of many people in the last 40 years or so, in particular Caucher, Scheber-Baron, Alexiev, Fivek, and many others are involved. All these say that, in fact, not only you can parameterize this object by a finite type space, but you can do it in a precise one-to-one way. In other words, you can find a space where every point precisely corresponds to one of these objects. And in algebraic geometry, we call these spaces moduli spaces. So in other words, there exists a moduli space for all these negative curvature spaces where you fix the value and the dimension, of course. And this statement, I mean, is proof, relies on many things, in particular the machinery, the whole machinery of birational geometry. And then the next is essentially saying that you can do something similar in some way for Calabi-Yau spaces, those with trivial curvature. Now, on a Calabi-Yau space, there is no positivity, there is no canonical positivity. There is, of course, positivity, but none of them are special in any way. There are just infinitely many positive line bundle, and none of them seem to be anything special. So in practice, that means you have to pick one of these positive divisors, and then you can try to understand them. So one of the statements in this direction is that I think that this probably sounds a bit, if you are a birational geometry, you probably know. If not, it may sound technical. So let me go to the next one. The next one says, similar to the negative curvature spaces, if we fix the dimension and if we fix the size of this polarization or the positivity that we have on our Calabi-Yau, then again you have a finiteness statement. Of course, the key issue here almost always relate to singularities. This is the same also in the negative curvature case. Without singularities, everything will be kind of simpler. And then from this, you can derive, after work of many people, you can derive that if your positivity is given by an effective divisor, then you can indeed again construct a moduli space of this sort of spaces. So if you look at Calabi-Yaus with a positive divisor and you fix the size of the volume, then you have finiteness, but in addition you have moduli space. And this was conjectured by Caucher and Zhu. And then the same story goes to minimal models. So I think even the experts, not everyone is probably familiar with this. So let me talk about it. It may look a bit annoying for the totally non-experts, but there are already quite a few experts here. Now we try to do something similar for minimal models in general. I am not even going to define what is a minimal model. So suppose we look at the world of minimal models. These are some of the main outcomes of the minimal model program. And conjecturally, at least, they come with a Calabi-Yau fiber structure, unless they are of general type. And then here we can define some kind of stability by, again, by picking some positivity. So I have this minimal model X. It comes with this fiber structure X to Z defined by the canonical divisor. And then if I pick a divisor A, where the A, we take it to be effective, so that this A is positive relatively over the base, and I call these things stable minimal model. Now you could also take A which are not necessarily effective, but then the moduli problem would be different, and then you will have a different statement. But you can actually do also. And then, similar to the general type and Calabi-Yau cases, if you fix Armand invariance, then you have finiteness and also moduli spaces. So let me say a few words about what you fix here, because it looks kind of quite different from the other classes. First, you need to fix the dimension. This is completely natural. And then you fix a positive rational number, and you fix a polynomial. This polynomial does not appear in the other cases. This kind of comes up in this more general setting. And then you look at all the stable minimal models where the dimension is D, and the size of the positivity, in other words, the relative volume, is given by this number U. And interestingly, this polynomial comes into the picture in the following way, that you take the canonical bundle plus a small multiple of this divisor A, and you just calculate its volume. If you take T to be small enough, what you get is a polynomial on the left side. And the condition is that this polynomial should be given by sigma, by our fixed polynomial. So this is a kind of numerical condition. In fact, you can translate this into an intersection, purely intersection number statement. It just tells you the intersection numbers of K together with A. So you have a range of intersection numbers. And fixing sigma means fixing these intersection numbers. Then the statement, as I said, is that all such algebraic varieties are parameterized by a finitized space, and moreover, there actually is a moduli space for them. If we take this A to be effective, we have a compact moduli space. If we don't take it effective, then you only get a quasi-projective moduli space, and in almost all cases, you cannot compactify in any meaningful way. And just again for the experts, the nice thing about this story in the minimal model case is that almost everything I say so far comes together in this picture, which from the first sight doesn't look like related. But in fact, all the results I've more or less mentioned about Fanos, the global case, about the Calabi-Yaos, about the general type, about the generalized pair theory, and many other things, all of them play crucial role. You cannot like remove any of them. So everything comes together in one place. And finally, let me just mention a couple of problems for the experts. Well, I will try to explain a little bit to the non-experts as well. One of the top problems in this field is called the abundance conjecture. It is actually already hidden in the minimal model conjecture that I mentioned. It's part of that conjecture, but now I state it more precisely. It says that suppose we take any smooth projective variety of any dimension where the canonical bundle is pseudo-effective. Pseudo-effective roughly means that it's a limit of like positive divisors. This is a numerical condition. And then the statement is that you can actually turn this into a geometric statement, a geometric condition. So you go from a numerical property to a geometric property. And it says that the Cordara dimension of X should be non-negative. In other words, if you take high enough multiples of the canonical bundle, you should be always to find sections. This type of statements are very hard to prove. So this is a well-known problem in the field. It has been open for like 40 years. There is proof in dimension 2 and 3, but almost nothing is known in dimension 4 and higher. But the good thing is that if you have this, in fact, it basically implies the minimal model conjecture. Another top problem, I'm going just to talk about two problems. Abundance, everyone in the area knows, maybe not everyone outside algebraic geometry, but it's really one of the most important problems. And we, birational geometers, we are not very good in advertising our area. Actually, we do a very poor job because we have this type of extremely important and very hard problems, and not many people outside the field know about them. And I think the reason is because we just don't talk about them enough. We like have to explain to the public why these problems are important. It's not only that they are extremely hard, but it's also what they tell us about these algebraic varieties. What they tell us, it's not only from the algebraic geometry point of view, it also tells you exactly the same thing in the differential geometric setting. There also you have the same question, but as I said, we don't do a good job of advertising these things. These are really very, it should be among the top problems in mathematics. Another even less known problem is a conjecture of Shakurov, which roughly speaking, it says that we have this Fano variety that I talked about, and then you have relative versions. You have Fano varieties over a base. And then this conjecture says that you can understand the anti-canonical systems even if you multiply in some kind of finite way. There is some finiteness again about these spaces. Although the range of possibilities is extremely large, but still there is some type of finiteness statement. This problem is also extremely difficult. I think I would put it at the same level as abundance. These two should be considered the top two problems in birational geometry because of their difficulty and because of what they imply. Both of them imply extremely strong statements. So to be more precise, this says that there exists some divisor such that xb it has this nice scaled singularities, and n times kx plus b is torsion or linearly trivial over any fixed point on the base. That's the content of the conjecture. Now, if we take z, this base space, to be a point, then this statement is equivalent to one of the first theorems that I mentioned, the so-called VAB. If we take the case when the dimension of x is more than dimension of z, in other words, you have a fiber case, then is more or less is what I mentioned about Fano fibrations, or at least they are not exactly equivalent, but that's precisely what you need to understand them. But the remaining case is when this map is birational. In fact, even when this map is identity, this is still an equally difficult conjecture. So what that means? That means if x to z is just the identity map, it means you are looking at the germ of a singularity and you are making a statement about this germ of singularity. But as I said, there are many kind of sub-cases of this. You take the identity, that's just one case. And then the birational case, it also divides into several possibilities and so on. So I just want to tell you, this is a really hard problem, and it is really important. And hopefully, in the next decade, maybe we can understand this final case of this conjecture. Anyway, there is a weaker form of this, which was already known. I think I will stop here. So apologies to those who are not experts and kind of were not familiar with the terminology.